Okay,
Okay,
so
so
um, the last class I had concluded with this two equivalent definitions of submodularity. I left you with a interesting problem to prove. Did anyone have a go at it? So there were two definitions of submodularity. The first one, which we built upon um, the concavity property applied to discrete functions, which is diminishing returns, right? And the second one was basically the union intersection property. So what we wanted to show was that diminishing returns property is equivalent to the union intersection property. Right. The first one is this diminishing returns, A union S. Okay. So, as I said, this is a very canonical example because in proofs of this nature, including guarantees, approximation guarantees on greedy algorithms, a lot of it is about constructing sets. Okay, so we had constructed some sets, right? What did we do? We said we are going to look at A, look at B, identify region that is in the intersection, identify region that is A minus B, identify the B minus A part, right? And we gave names to all of these. The proof method was to construct these regions, write down differences, right? Successive differences between, let's say, the union of the whole thing minus one element removed from the intersection, right? So that's how we think, right? When we try to prove some inequality like this. So we need to do that and basically construct the left-hand side or a scaled version of the left-hand side as a sum of many such differences. The moment you bring, right, into this nature, sum of differences, that's when you can apply the diminishing returns property, right? So we'll just show how we do that. Did anyone have a go at it? I give some hint also. So what did we do? We basically wrote these steps. A intersection B, we gave it a name, right? We call it X. So this A intersection B, we gave it a name X. Y and Z were the names of these differences. And then you also considered, so just stay back if I request, because towards the end we'll, just please stay back. Because we are also supposed to do this course evaluation. So just by last 5 minutes, I'll step out course evaluation. So we'll have to construct from this structure like this. So we will consider X union all elements in Y. Okay, X union all elements in Y minus X union all but one elements in Y. Right. So as I was saying, we'll construct this X union all elements in Y, which would amount to A, right? X union Y is nothing but A minus f of X union Y1 to Y, whatever, n minus 1. All but one element in Y. Why do we do that? Well, we do that because this can benefit from diminishing returns. In what way can it, what will be our A here? So let's give some different name to this A and B. So let's just call it P Q, right? So what would, if this A is our P, sorry, X is our P, right? Or I mean, you could even think of, yeah, you could even think of X union of all the elements. So somewhere you'll have to consider successive differences tree. From the successive differences, reconstruct this difference. So any thoughts? How would you do that? This is very tempting, right? You're just looking at successive differences. How do you benefit from the diminishing returns inequality? Yes, anyone? This is where we left off last time. I mean, what I'm doing for A, I can do for B also. Same expression I can write for f of Z union Y. I'm writing this for X, that is A minus B. I can write this for Z, which is B minus A. I've just given it also names. I've just said this is f of X plus, see, you understand what is happening here, right? The successive differences eventually all will get cancelled out, except even the f of X will get cancelled out, right? Except f of A, because f of A is f of Y union X. This is f of A, right? So only this term, eventually only this term will remain. This will remain, this will get cancelled with its next difference, and so on, and f of X will get cancelled with the negative component of the final term. You understand what's happening? All terms will get cancelled out except for this guy. So if you want, I'll highlight that as well. This is nothing but A. Likewise, this is f of A. Likewise, f of this term is what is f of B. Okay, so all the other terms will get cancelled out to subsequent differences. This is clear? So my question was, from here, how do you proceed? So this f of A is f of X plus blah blah blah, can also be written f of A is f of X plus delta Y. This is the deltas of the Y's. F of B is likewise f of X plus the deltas of the Z's. So what's the next step? Anyone? How do I get into this form? What is this form saying? This is basically also looking at what is the difference between the argument on the left and argument on the right? How many elements? Exactly one element, right? So this difference is exactly of this form, isn't it? That's the reason we have written it in this form. There's each difference. Ultimately, most are getting cancelled out except for this one. But I wrote it in this form so that I can look at these differences from the lens of diminishing returns. Okay. The question will be, what will be, if it's P and Q, what will be our P and Q here? Right, so can we apply diminishing? Actually, that's what was our goal? Our goal was to prove that, or rather, can we recover? Not apply, can we recover? Okay, what do you want to do? What did we set out to do before that? We can. So what did we set out to do? So we are assuming that, sorry, we are assuming that we have the diminishing returns property, and we are trying to show f of a plus b is greater than f of a union b plus f of a intersection b. So we can actually apply this. Okay, so we are not trying to recover, we are rather trying to use this inequality. So I can use this inequality. Then my question is, what is p, what is q here? Anyone? Can I just treat f of y union y union x union y1 y2 y n minus 1 or whatever to be my p, my yi to be the s, right? And x union this entire thing, which is p, of course, should be a subset of q. So what should be my q? This. So let's say p is x union y1 to pi k minus 1, whatever, right? So p is this s is yk. So what is my q? Okay, what is q? P should be a subset of q. So that the left hand side, which otherwise is just f of a or f of b in these two cases, can give me an inequality. I want a less than equal. I mean, actually, I want a greater than equal to. Yeah, I want a greater than equal to. Right? Or should it be the other way? Should I consider this to be should I, instead of this, should I consider this to be q, this entire expression to be q, and s to be yk? What do we want to do? We want to show that f of a plus f of b is greater than equal to f of a union b, blah, blah, blah. Right? So should this expression, right, this difference, should it be f of q union s f minus f of q, or f of p union s minus f of p? That should be very clear to you. What would you desire? Q or p? On the right hand side, we're looking for f of a plus f of b, right? So on the left hand side. So the right hand side, we would like to have a greater than equal to. So what should it be? Should it be p or q? Yes? P, right? This should be p, right? What I wrote earlier. Is my question clear to everyone? So all these are arguments you can have in your head. So you would like this actually to be p. Okay. So what have I done here? of the remaining part, the delta x or delta y, uh, which are those subsequent, some of the subsequent differences, is what I'm trying to lower bound. So what I do here is we are basically adding those subsequent elements. They should only give you diminishing marginal gains. So on the right hand side, what I do is instead of x union y1 to yk minus 1, which is the P, now if I have Q set to x union entire y, which includes right yn or the last element as well, and also includes z, the part in B which was not in A. If this is my Q, right? Obviously, from there you can subtract out the last element zi if you want. In fact, no, not last element zi. I'll subtract out the yk. This element yk. I have to have the consistent element set out, subtract from both. So you'll find that this entire left-hand side, if you just set Q to be x union y union z, right? Instead of x union y, I have x union y union z. The set has grown. The same element is being added to both left-hand side and right-hand side. Therefore, you have this inequality by this property. You can do the same thing on the other hand, right? So if we are considering y union z instead of x union z, then I set my Q again to be x union y union z. You see the trick here? So you'll get delta or the sum of those delta, sum of those differences greater than f of x union y union z minus f of x union z in one case, and the other is with respect to y. So when you add both the inequalities, you get what you want. Basically, x union y union z is nothing but A union B, right? You'll get this 2 times x of x union y union z minus f of x union y and x of x union z. But what is x union y and x union z? X union y is A, x union z is B, right? This is A and B. So you actually find, so just continuing this expression further, right? So this is what you'll find. Sorry. Yeah, here. F x union y is A, f of A, f of x union z is f of B. Okay. And what about the intersection? A union B is nothing, A intersection B, sorry, is nothing but f of x, right? So this x is what will be remainder as you keep, sorry, this part, right? As you keep eliminating elements from y and z on the respective terms, the only term that will remain is f of x. So f of x will be shifted to the right hand side. This is f of x. F of A intersection B is f of x. This is what we already found, f of A x union y union B, union z. Okay. So I hope you got an idea of how this proof is done. It's a fairly straightforward algebraic manipulation. If you go through my last year's recordings, you'll find the proof which involved, the approximation guarantee for the greedy algorithm, not very different from such manipulation. Okay, so there are many other properties which obviously we won't have time to talk about. Maximum of submodular functions, if they're submodular or not, right? But max is not submodular in general. Okay, and so on. We will unfortunately not have time to talk about the algebra of submodular functions. I'm going to stop with this. This last slide. One of the very interesting compositions is the concave over submodular. So if you take a modular function even, let's say cardinality, and put a square root of cardinality, right? The square root of cardinal, what is square root? Is it convex or concave? Sorry? Concave. So square root of a modular function, you can verify that it's going to be submodular, right? So in general, concave over monotone submodular functions are submodular, and in fact, specifically given a positive modular function, a concave function G applied to the modular function M of S is submodular. Okay, so there are a whole bunch of functions which are feature-based functions, and this is one of the reasons why feature subset selection becomes a very interesting submodular maximization problem. You're trying to find a bunch of features that maximizes some external likelihood over those features. Okay, so yeah, unfortunately, we'll not have more time to talk about the optimization. I just wanted to give you a flavor of one such proof methodology. I can refer you to maybe 2 years back when I wasn't doing course projects. So I got a lot more time to maybe at least 5-6 lectures. So I'll refer you to the course videos 2 weeks from 2 years back. But I assume that through the projects you have got sufficiently more exposure. Whereas you can't get everything. So I assume that the projects give you a lot more exposure to the range of optimization problems. And as you know, the area is so evolving. The nature of problems, the space in which these problems are applied, the scale at which they are being applied is also. And by the time you have the next version of this course, things are going to be even more different, right? So I think it's important to get the elements correct and here a whole range of the spectrum of emerging problems which all of you have from each other. So I wish you all the best for your course projects. We can of course have some discussion on your course projects right now, but you need to do that individually with me. Before that, I request I'll just step out. I'll request you to just fill in the